Hi everyone, welcome back to Dave's Math channel. This is my fourth video in a series on complex numbers, and today I'm going to talk about complex multiplication and division. And so let's begin. Um, so I already taught you how to add two complex numbers, that's shown on the left. And multiplication is kind of similar. It's a little more complicated, but the way you're supposed to think of it, just think of FOIL. I mean, think of how you learned how to multiply binomials in algebra. I mean, this is kind of the hard way. So you can use a distributive property twice, right? You can break up c plus di into c. So you have two terms here. C times A plus BI plus DI times A plus BI. And then you just multiply term by terms. And so you get AC plus BCI plus ADI plus BDI squared. But we know that I squared is -1, so we can write that as minus BD. So when you're done, you get AC minus BD plus the quantity BC plus AD times I. That's kind of the hard way to do it, but that's a step by step. And it's easier if you remember the FOIL rule, which you probably learned, in high school when you were learning algebra. So, first out or in or last. If you use that rule, you get the same thing. But just remember the last terms gets you BDI squared, which is the same as minus BD. So that's how you get it using FOIL. And here's an example. Say you want to multiply 3 minus 2i times 4 plus 5i. And I guess here they're doing it the hard way. They're breaking it down term by term. But I'm not going to go through all the steps. But when you're done, you get 22 plus 7i. That's using, I guess doing the distributive property twice. That can be done more easily using FOIL, or if you just memorize a formula. I recommend FOIL. But anyway, and then there's also a geometric way to interpret the product of two complex numbers. And this one is actually shown in polar form. It turns out that if you use the polar form, remember in the last video I showed you that there's two forms of representing a complex number, either Cartesian or rectangular form, which is x plus yi, or polar form, which is r times cis of theta, if you like, cosine theta plus I sine theta. And here they're using the polar form. So this is really nice. It turns out, and I'm not going to prove this, but it turns out that if you have two complex numbers, shown here, represented in polar form, you don't even have to represent them in polar form. But if you just have two complex numbers, which just look like vectors in the complex plane, then the way you're supposed to interpret the product is you've got two angles here. For your first angle is theta 1, your second angle is theta 2, and it turns out the angle of the product is just the sum of those two angles, theta 1 plus theta 2. And the other thing is that the absolute values multiply. So just remember the absolute, so you have, your first complex number Z1 has absolute value R1, that's just the length, if you think of it as a vector. And then Z2 has absolute value R2. And then it turns out that the product Z1, Z2 has absolute value R1, R2. So absolute values multiply and arguments add. That's kind of the rule for multiplying complex numbers in polar form. Very nice rule, easy to remember. And it turns out that actually does, both of these formulas for multiplying two complex numbers are equivalent. I'm not going to show that here. It's a little bit messy, but anyway, it's true. Just take my word for it. If you want to do the derivation yourself, you're welcome to, but it involves a lot of pretty messy trigonometry in algebra. Um, but you can do it if you want. And so then that kind of takes care of complex multiplication. But there's a special case of complex multiplication that's very interesting and very important. What happens when you multiply a complex number by its complex conjugate? So you've got an arbitrary complex number here, a plus bi. A and b are just arbitrary real numbers. And so you want to multiply it by its complex conjugate, a minus bi. Well, if you do that, it turns out that you always get a real number. As a matter of fact, there's always a non-negative real number. It's equal to a squared plus b squared. I think I mentioned this last time, actually, in the last video. So notice that a squared plus b squared is nothing but the square of the absolute value of the number. of a plus bi or a minus bi. They both have the same absolute value. This is another case of absolute values multiplying, by the way. And then it also turns out it's real, which means the argument is 0. And actually, this is another case of the rule for adding arguments. I mean, if the argument of the first complex number a plus bi, you call that theta. Theta turns out to be the arctangent of b over a, but that's not really that important here. But then it turns out that the argument of the second number, a minus bi, is minus theta, which is arctangent of minus b over a, which is the same as minus arctangent of b over a, since the arctangent is an odd function. So yeah, so the arguments are equal and opposite, and so when you add them, you get 0. So just just to think about the complex, the rule for multiplying two complex numbers in polar form, and then you'll see that this is a special case of that. And this is a very useful rule. And why is it useful? Well, one reason it's useful is what if you want to, well, anyway, let me start with an example. So say you want to multiply the complex number 5 minus 2y by its conjugate, which is 5 plus 2y. Well, you can do all the steps if you want. This is using FOIL. Might as well go through it using FOIL. So first is 5 times 5, that gives you 25. And then you got outer, gives you 5 times 2y, that's 10i. And minus 2i times 5 gives you minus 10i. And then minus 2i times plus 2i gives you minus 4i squared. Well, you can see that the terms in the middle cancel. You got plus 10i and minus 10i. That gives you 0. So there's no imaginary component. And then minus 4i squared, since I squared is minus 1, this is just minus 4 times minus 1, which is plus 4. So in the end, you get 25 plus 4, which is 29. Pretty neat. So anyway, that's just an example of that. And you always get a positive real or non-negative real number when you do this. It's just the square of the absolute value of 5 minus 2i in this case. So that's how you multiply two complex complex number by its complex conjugate. And why is that useful? Well, it's useful if you want to divide two complex numbers. This is probably the most complicated arithmetic operation we do in complex analysis. So say you want to divide the complex number a plus bi by c plus di. Well, there's a trick for doing this, and the trick is to multiply both the numerator and the denominator by the complex conjugate of the denominator, because that'll give you something real in the denominator, right? In the end, you want to get a denominator that's real. So if you do that, remember that c plus di times c minus di is just c squared plus d squared. So if you simplify the denominator of the line on top, you get c squared plus d squared, and then you just use the rule for multiplying two complex numbers, which we learned, or I went over at the beginning, and then you get this thing, ac plus bd plus the quantity bc minus ad times I. So if you want to write each component separately, you just divide each term in the numerator by the denominator. So the real part is going to be ac plus bd over c squared plus d squared, and the imaginary part is bc minus ad over c squared plus d squared. Pretty neat. So that's a formula for the quotient of any two complex numbers given in rectangular form, and the result is also given in rectangular form. And I don't think it's worth memorizing the formula. I think it's worth deriving it like they did here. And here's an example. So suppose we want to divide 6 plus 3i by 5 plus 2i. Well, they just do the same thing they did before. I'm not going to go through all the steps. The first step is just multiply the numerator and denominator by the complex conjugate of the denominator, which is 5 minus 2i in this case. And when you do all the math, when you're done, you get 36 plus 3i divided by 29. That's the answer. And notice that this 29 is just the square of the absolute value of 5 plus 2i. So anyway, that's an example. You can check it for yourself. And what else do I want to say? Oh yeah, and then in polar form. Remember I showed you there was a nice polar form for multiplying two complex numbers? Well, it turns out there's also a nice geometric interpretation of the quotient two complex numbers. This thing they're writing, I mean, so this is the polar form of Z1 and Z2 here. Say Z1 and Z2 are two arbitrary complex numbers. I guess Z2 has to be non-zero, but in this case, they're both non-zero. So we can write Z1 as R1 times cosine theta 1 plus I sine theta 1, or you could just write it as cis theta 1. I'm just going to call it cis theta 1 to simplify matters. So Z1 is R1 cis theta 1, Z2 is R2 cis theta 2, and then it turns out if you do the math, the answer you get for Z1 over Z2 is R1 over R2 times cis of theta 1 minus theta 2. So this is kind of like the rule I told you for multiplying two complex numbers in polar form. So the only difference is here we're subtracting the arguments. We're dividing the absolute values. So when you divide two complex numbers, z1 divided by z2, the absolute value of the result is going to be the quotient of the absolute values of the numbers you started with, just r1 over r2, and the argument is going to be the difference, theta 1 minus theta 2. So it's kind of the same rule as for multiplying, except the instead of multiplying the absolute values, we're dividing them, and instead of adding the arguments, we're subtracting them. So anyway, um, that's all I have to say for today. That completes my lesson on complex multiplication and division. I hope you enjoyed it. Thank you for watching. Long live math, and I'll see you next time.